All right, so first at t equals 0 minus, so this is just before the switch is going to close. The rest of this circuit has been connected for a long time, and so here we have an open circuit because it hasn't been connected yet, but we still have a circuit along the outside of this, and so over time this inductor will turn into look like a short circuit, and the capacitor will look like an open circuit. So actually, once we figure that out, this current that I said is the connection that I'd say is along the outside. Over a long period of time, it turns out we have an open circuit here, and so that actually there's no current actually flowing anymore at t equals 0 minus through this circuit. And so if there's a 12-volt voltage source here, there's no current flowing through either of these resistors, this one or this one, then the VC here must equal 12 volts. All right, next, let's look at the circuit for t equals 0. Now, I was saying here capacitor side because once we close this switch right at t equals 0, we have a short circuit. And so what we've done here is we've created kind of two separate circuits here because the current from this circuit is going to just be shorted out and go through the short circuit, and the circuits to the other one is going to do the same thing. So we kind of have two separate currents here, separate circuits here. So I'm going to do the capacitor side first. That is this side. The capacitor was at 12 volts right before the switch was closed. So I'll say at t equals 0 minus, it was at 12 volts. So at t equals 0, it will start to discharge. And it's only going to discharge into this 4 ohm resistor since that's all it's connected to. So now we can say VC of 0 is equal to 12 volts. And we can also find the current at going through that capacitor right at t equals 0. We can find that according to Ohm's law. So we have 12 volts and there's only a 4 ohm resistance in that part of the circuit. So we're going to get 3 amps, but we have to be careful about the direction. This capacitor has energy stored in it. It has 12 volts stored in it. So when it starts to discharge, remember that the direction of the current changed. So the current actually in this part, I'll just cross this out. Oh, that's the positive current direction. The actual current in this part of the time is going to be flowing in the opposite direction. It's going to be discharging. It's going to be acting like a source. So it looks like a source of energy. And so the current in this case, if we choose the downward direction is, I'll say is the positive I direction, that was what was marked, then it's going in the opposite direction. So I'm going to have a minus sign there. The current at time equals 0 through the capacitor and through that resistor as well is going to be minus 3 amps. Then on the other side, we have a short here at time t equals 0. This is the inductor side. IL of 0 is 0 amps right at time equals 0, but it's going to start increasing. And the B field is going to start increasing. So we're going to get a large EMF, that electromotive force, what it tries to resist that change. And so the voltage then will be large because it's resisting that change. The voltage here will be 12 volts, which is equal to our source voltage. It might help to look at those plots where we had we connected an inductor to a voltage source. It got up to Vn and then it started to decrease. So it might be helpful to look at those plots as we discuss these. All right, then lastly, we can draw our circuit for time equal infinity. In this case, the switch is closed. It's been closed for a long time. So now we have a short circuit across the inductor, and we have an open circuit across the capacitor. Now in this case, the capacitor is done discharging. It had some energy stored up, and then it started to discharge in that resistor, so now it's done discharging. So VC at infinity, all that voltage is gone, and there's no more current flowing because all the energy has dissipated. So that's also equal to 0. And then on the left side, we still have a circuit. It's a voltage source and a resistor, and this is shorted and this is shorted, so that's all we have in this circuit. It's just a voltage source and in the resistor, and nothing is changing at this point. So we have these equations. They're the voltage for the inductor over a long period of time will be 0 because the currents aren't changing anymore. And to get the current, since the inductor is a short, the current going through that inductor will be equal to 12 volts divided by 3 ohms, and we get 4 amps. And that concludes our example.